Okay, before we look at the next topic, so let me conclude with the proof that Euclidean algorithm works correctly. Okay, so I'll go over the proof really quickly. Okay, so first of all, when you call Euclid, if x is less than y, the first time you call it, the argument swap, right? If x is less than y, when you call itself, it's called like y and x mod y, and then if x mod y, if x is less than y, will always be equal to x. So after that, x is always larger than y. Okay, and you can prove that if x is larger than y, Euclid xy is going to be equal to GCD x or y. Okay, I'm going to prove that really quickly. Okay, first of all, if y divides x, then GCD of x, y will be y. So in the best case, the algorithm is correct. Otherwise, it make a call. Okay. So when you wanna compute Euclid xy, the algorithm calls Euclid y x mod y. You recall? So it gives the second element as the first element and the mod. The first element mod the second element as the second element. So we want to prove that to show that Euclid algorithm works correctly, we need to show that GCD of x and y equals Euclid equal this function, the result of this. Okay, we can do that by induction. We prove by induction on the arguments. So we assume that Euclid y x mod y return the GCD of y x mod y. So this is the induction hypothesis. We assume that Euclid y x mod y equals GCD of y x mod y. Okay. So now we want to show that Euclid y x mod y equals GCD x y, right? But we know that by induction that Euclid y x mod y equals GCD y x mod y. So the recursive call gives the correct result. So what we need to show is like we need to show that GCD xy equals GCD y x mod y. Okay, but this is true because we have already proved it. Okay, so what is x mod y? X mod y is basically this number. Okay, it's gonna be some x, and you divide x by y and you round down. So you throw away all the decimal places. And then you subtract. So this is the remainder x mod y. Okay. So if the number, we have already proved this. So if a divide x and y, a also divide x mod y. That was the homework. So x mod y is x minus some number, right? X over y times y. So if a divide x and a divide y, a also divide this because it divide x and it also divide y, right? So we want to be able to show that GCD is the same. Okay. Reason for that is that if I'll go quickly. So if g divides x and g divide y, then g is gonna divide x mod y. Okay. On the other hand, if g divide y and g divide x mod y, g is gonna divide x. So the GCD of x and y is gonna be it's gonna be a common divisor of y and x mod y, because for any number that divide x and y, it also divide the mod x mod y. So the GCD of y x mod y has to be at least the GCD of this, because any GCD is going to be a common divisor on that. On the other hand, if the GCD of y and x mod y, it's going to be common divisor of this as well. Because if you divide y and you divide x mod y, you also divide x. Okay. So with these two statement, you can conclude that the GCD of these two pairs of numbers are equal. Okay, so so I'm gonna go really briefly just this. So the first argument, if we know this, so this implies that this means GCD of y x mod y is going to be at least GCD xy, and this second one is going to imply that GCD of x mod y is going to be at least GCD of y x mod y. So this is x or y at least this, GCD at least this. So if you have both statements, then it implies that the two numbers are equal. So I'm gonna go really quickly at this, but the proof of this we already did. Okay, so if you recall when we give you this, right? So this is A, this is B, and this part is A mod B. So if you divide A and B, you need to divide A mod B, and if you divide B and A mod B, you also divide A. So this is like the pictures. Okay. So I'm gonna go really briefly as this. If you need more details, I can post the video clip from last time, so you can watch. Okay. We don't have time for this now. All right. So that's it. This is it for GCD. So we'll start. We'll look at the next topic. Okay. We have 1 hour.